Okay, into the final video for the interference of light topic, and sorry, just fix that up. And we're going to look very briefly at speckle, and then we'll look at compact disc and this concept of, in particular, all types of data storage, optical data storage using lasers. So let's get into it. So let's talk about speckle. I think speckle would have to be the most trivial concept that's in the Year 12 physics course. One of my aims as a writer for the new course was actually to take it out, because I don't really think it's all that scientifically important or interesting. But basically, when you shine laser light at any supposedly flat surface, it's never going to be completely flat. So you're going to have lumps and bumps and all that sort of thing. And basically you have this interference pattern between the incident light and then the reflected light that goes back, and that interference pattern is constantly changing. So that gives you that impression that that laser speckle is sort of constantly changing in intensity. So that gives it that sort of constantly changing sort of nature. It doesn't just look like a fixed light on a surface. So yeah, speckle is caused by interference between the incident and reflected light, and light that's going in different directions on a rough surface. So now let's get into compact discs. Been a bit lazy here, and I've just photographed the page out of my notes because couldn't be stuff writing out this all again. Firstly, I think it's really important that we understand what digital data is. So digital data is where we store data as either ones or zeros. So we talk about digital music, we talk about digital TV, digital radio. So it basically sends a series of numbers, if you like, sent as a series of ones and zeros. If you're interested, I think a byte is 8 bits, and a byte is basically a combination of 8 ones and zeros, and that's the basis for all numbers, characters, all that sort of thing in computer language, as well as lots and lots of other things. In the old days, we used to have analog data or analog signals, where we actually looked at variations in either the frequency or the amplitude of the waves, and we used to interpret that. And if we got a bit of interference on those signals, we tended to just go a little bit fuzzy. You know, your TV would go fuzzy or your radio would go fuzzy. But with digital data, if you don't get the ones and zeros, you basically get no signal. That's when your TV freezes sometimes when you're watching something on TV, because it loses that data. It doesn't know what to put there because it hasn't sort of got like a partial signal. It's either got it or not. And that's all coming in as basically a series of ones and zeros. If you're interested in digital data, I'll let you go and look more into that. So let's talk about, on a CD, how this works. So on a CD, we've basically got, and we can either look at this cross-section view here, or we could look at it from the top, and it basically consists of a flat area with a series of pits going along on the track. So this would be a pit, go down and come up, then go down, then come up, and we've got this up, down here. And the way it actually is read is if there's no change in intensity, it reads it as a 0. If there's a change if there's no change in height, we'll get to why there's a change in intensity in a sec. If there's no change in height, it reads it as a 0. If there's a change in height, it reads it as a 1. So it's not whether it's up or down, it's whether it changes. So here it's up and it's a 0 because it hasn't changed. Here it's down and it's a 0 because it hasn't changed. But on all these spots where the height changes, we read that as a 1. So how does it read it? Well, the depth of these pits here is 1/4 of a wavelength. So that means that the reflected beam that comes down here and then gets reflected up will have travelled 1/2 a wavelength, and it'll be 1/2 a wavelength out of phase with the incident light, so we will get destructive interference. So there's light coming down, constant phase relationship, light reflected here. When it gets to this point, they're going to be 1/2 a wavelength out of phase, so we get destructive interference. Destructive interference will mean that light will be dulled, or in a sense, if it's complete destructive interference, that light would, if you like, disappear. So then, as I've already said, when it sees a change in intensity, so everywhere the height changes, it'll see a change in intensity as you get interference between the reflected light and the incident light. It'll read that as a 0, and it'll read that as a 1. All the others are read as a 0. So that's, if you like, the concept of how the data is, if you like, read from the depth of the pits, and interference, because they're a quarter of a wavelength deep, hence the reflected beam travels half a wavelength and interferes with the incident light. Secondly, we need to know how it keeps on track, because we've got this long continuous track of pits or bumps and land, which is the area in between, on a CD. And it needs to have a way to know that it keeps tracking along on the right track. So, it does this through a fairly neat and novel way using a diffraction grating. So, the laser beam, after the laser beam, there's a diffraction grating, and that splits the laser beam into 3. So we have the bright central one, and then we have these 2 little beams on the side due to the interference pattern created by the diffraction grating. And as it tracks along, it monitors this middle laser, which tells it about the 0s and the 1s, the digital data, but this top laser, top trailing one, and this forward leading one are also monitored. Now, if when this is travelling along, this bottom and this top one don't change, they're on this flat area, then the CD knows it's on track. However, if the laser starts to get too high, you'll see that this leading laser starts to hit the pits. So there'll be a change in intensity of this one. So if this front one changes, it knows, oops, we've got to move the laser down to correct and get it back on track, like over here. Also, obviously, hopefully obviously, if this top trailing one starts to hit on the tracks, so there's a change in intensity as it starts to hit the pits, then it knows it's getting too low, so it needs to move the laser up. So basically this laser uses the interference between the incident and the reflected light and a transmission grating to create 3 dots instead of 1 to basically read the CD, or a DVD works in a similar way, and also it uses that to keep it on track. Just out of interest, a lot of CDs now that you burn your own CDs and or DVDs that you might buy, or you might burn your own DVDs, even though I must admit with solid state drives people are not doing that anywhere near as much. It doesn't always work with the pits. A lot of those burnable CDs basically just change the reflective nature of the surface, so whether it reflects the laser back or it doesn't reflect the laser back. So it's a bit like painting it black so it won't reflect the laser, or leaving it silver so it will reflect the laser. That's a bit of a simplified model. But when you burn a CD on your computer, you're not really burning these pits in. This is what happens with sort of pre-pressed CDs. However, the effect in terms of it seeing changes in intensity and using that to read 1s and 0s is the same. I think I've raved on a bit longer than I was going to about that. I hope I haven't confused you, but probably look at what's on the paper and that might make more sense than maybe what I've been saying. Cheers.